In lecture 24A of Differential Equations in Linear Algebra, we're going to be summarizing some things that we've learned from our examples dealing with eigenvalues and eigenvectors. We're going to give a partial summary of the behavior of two-dimensional linear systems of differential equations based on eigenvalues. I did talk about that at the end of 23A. I want to talk about it again here in 24A. Then we're going to go back to the harmonic oscillator model, the unforced model where there's no external forcing. And we're going to look at the four main cases: undamped, underdamped, critically damped, and overdamped cases based on the amount of damping, which is the amount of friction. These are the main things that can happen, though in real life it's really only the underdamped and overdamped cases that we actually observe. You can see what the topics are also in lecture 24B, very important linear algebra topics that you won't want to miss. All right, so let's go into our partial summary of behavior for two-dimensional systems based on the eigenvalues. I did essentially show you this slide again in lecture 23A. For a two-dimensional linear system of this general form, where this is your coefficient matrix whose entries are A, B, C, and D, we want to be able to find the eigenvalues. I told you last time, or maybe a couple times ago, that you can quickly jump to the characteristic polynomial. You don't have to actually calculate this determinant. You can just jump right from this matrix to this polynomial right there in either one of these forms. T represents the trace of the matrix. T is A plus D. It's the sum of the numbers on the main diagonal, A plus D. And D is the determinant of the matrix. D is AD minus BC, the determinant of a 2 by 2 matrix. You can see that here. We take lambda squared minus the trace times lambda plus the determinant. That will be the characteristic polynomial, which we, in theory, can factor always, but in practice that factoring can be difficult. Then we can say the following. The origin will be a real non-spiral sink if and only if, which I will abbreviate from now on, IFF, both eigenvalues are negative. And the implicit assumption here is that they are real as well. We only use inequalities like less than or greater than when we're dealing with real numbers. I will draw a complex number plane here, the complex plane, where the horizontal axis is labeled with the word real, and the vertical axis is labeled with the word imaginary. But remember, those are just labels. The imaginary axis is there. I did draw it, okay? They're just labels. You imagine this as being what's called the complex plane. You imagine the real axis here as being the actual real number line sitting inside the complex plane, meaning every real number is a complex number. Any real number A can be thought of as A plus 0 times I, where I is the imaginary unit, the square root of -1. Lambda 1 and lambda 2 both being negative means they are on the real axis and to the left of 0. Maybe lambda 1 is here and lambda 2 is there. Okay? That'll be helpful to think about as we go through this list here. Next one. The origin is a real non-spiral source if and only if both lambda 1 and lambda 2 are positive. In general, I'm not saying lambda 1 has to be less than lambda 2, even though I drew it that way. It could be the other way around. Lambda 2 could be less than lambda 1. That first example was a non-spiral sink. The second example is a non-spiral source when both eigenvalues are real and positive. They're both bigger than 0. I'm not saying necessarily which one is bigger than the other. The origin will be a saddle point if both eigenvalues are real and they have opposite signs. And realize here that this is excluding the number 0 as an eigenvalue here. So I'm not considering all cases. That's why this is just a partial summary. 0 is neither positive nor negative. It's its own special case. So when I say they have opposite signs, I mean one of them is bigger than 0 and one of them is less than 0. Coming back to this picture again, maybe lambda 2 is the one that's bigger than 0, and lambda 1 is the one that's less than 0. That could happen. In that case, we have a saddle point. The eigenvectors corresponding to these will correspond to straight line solutions. For the negative eigenvalue, that will correspond to straight line solutions heading toward the origin. It's a sink in that direction. For the positive eigenvalues, that will correspond to straight line solutions going away from the origin. It's a source in that direction. And overall, it acts like what we call a saddle point. Solutions generally curve. Well, if you start close to the line that's a source, they curve close to that line if you start closer to it, but then if they're not exactly on that line, they eventually move away. We've seen that. Next case. The origin is a spiral sink. I talked about this in 23a. If and only if we get complex, I should have emphasized in 23a, non-real eigenvalues with negative real parts. Real numbers are complex numbers, so I shouldn't just say complex, I should say non-real. And we have seen, I mentioned this before, when you have complex eigenvalues, non-real I should say, again, for a real matrix, they will occur in what are called complex conjugate pairs. If lambda 1 is this number right here, whose real part is A and whose imaginary part is B, where A is negative and B is positive in this picture, A is negative and B is positive, the real part is negative, you're to the left of the imaginary axis, and the imaginary part is positive, you are above the real axis, the other eigenvalue will be the reflection of that point across the real axis. Lambda 2 is called the complex conjugate of lambda 1. You write it as lambda 1 bar. In terms of the real part and imaginary part, the real part is the same, that's still A, but the imaginary part gets negated. So A is negative in this picture still. B is still positive, but negative B is negative. They're non-real eigenvalues with negative real parts. That's where you're going to get a spiral sink. For a spiral source, they're non-real with positive real part. So it's the real part, negative to the right, or excuse me, negative to the left of the imaginary axis, and positive to the right of the imaginary axis that determines whether it's a spiral sink or a spiral source. Hey, that kind of jives with the first two lines. These are real numbers, but if these are both negative, it's a non-spiral sink. If these are both positive, it's a non-spiral source. The real part of these other eigenvalues that are non-real plays the role in its sign, negative or positive, to whether you get a sink or a source. And we saw why that happened, at least with the sink example, with Euler's identity. In the case of non-real eigenvalues, the periodicity of the trigonometric parts of the solutions that involve cosines and sines is 2 pi divided by the absolute value of the imaginary parts. So, if these are your non-real eigenvalues here and here, the absolute value of the imaginary parts in both cases here, the absolute value of B, which is the same as the absolute value of negative B, is B itself if I assume B is positive. 2 pi divided by that is going to be the period of the cosine and sine terms in the formula for the solution. Okay? And we saw that. I'll re-emphasize it here now as we get into our harmonic oscillator examples. I call these unforced harmonic oscillators because there's no external forcing. The only forces acting on the mass on a spring, say going back and forth, are the restoring force due to the spring, with spring constant K, and the damping force with damping constant B. Those are the only forces. In Chapter 4 of Blanchard, Devaney, and Hall's book, we will get into what are called forced harmonic oscillators, where there's some external forcing. The nature of that external forcing could maybe be that you have the mass on a table that is going back and forth like this as the mass slides back and forth. That could be one way the external forcing could come into play. Another way that could come into play, which should seem harder, is you could maybe hit the mass with a hammer every so often. Okay? That should seem like it would be a more difficult thing to model, but we will ultimately see in Chapter 6 with Laplace transforms that it actually can be modeled. But here we are doing unforced. We can also call it a homogeneous equation. The right-hand side is 0. If you've got external forcing, that right-hand side will be non-zero. In general, it'll be some function of time, t. It'll be a non-homogeneous second-order equation. But because that's 0, we call it a homogeneous equation. That, again, corresponds to unforced, no external forcing. All right, what we've been doing with this Well, maybe 4 or 5 or 6 lectures ago as we converted it to systems and we looked at the phase plane. We could do that here, and in fact I will. But I want to show you that you can think about solutions to this without converting to a system and without looking at the phase plane. We did a little bit of that as well. By guessing, educated guessing. We have seen that sometimes an exponential function is a good guess. And that is the case here, even if the constant s has to be a complex, non-real number. Just as we saw for spiral sinks and spiral sources in the last lecture. Except that was a vector case. Here we're talking about a scalar equation. Second order, because it involves a second derivative. Well, does this kind of guess work? What happens when you differentiate and substitute? Again, s is a constant. It's an unknown constant. Take the derivative, use the chain rule, you get an extra factor of s. Take the second derivative, you get another factor of s. Plug it into the left-hand side of the differential equation and see what happens. Here's what happens. my double prime plus by prime plus ky becomes this. Each one of these terms has a factor of e to the st that can be factored out. So you have e to the st times, in parentheses, ms squared plus bs plus k. What do I want? In order for this to be a solution, I want it to equal the right-hand side, 0, for all values of t, no matter what t is. Well, e to a power is never ever 0. In fact, I made a terrible mistake on one of my grad school exams once, where I accidentally wrote e to the 0 equals 1, equals 0. I don't even want to write it down. E to the 0 does not equal to 0. That's never true. E to a power is never 0. Well, some people think e to the minus infinity is 0, but remember, infinity is not a number. My grad school teacher, who was kind of a crazy guy, wrote in big red letters on my paper, "What? Are you crazy?" That's the way he talked, too. And, well, yeah, it was a brain freeze. E to the 0 is not 0. E to the 0 is a 1. So this is never 0. So the only way this is going to be 0 for all t is if that's 0. But hey, that's a quadratic in the unknown s. I can use the quadratic formula to solve for s in terms of m, b, and k. And here's what you get. Okay, that's nice. We get this. So what? Well, now that is going to essentially mean e to the st will be a solution if s is one of these two numbers in general, unless the thing under the square root is 0, then it'll actually be just one real number. That's kind of a pain to have to plug that in for s. For my students, you should definitely practice the examples. Plenty of concrete examples with concrete numbers in the book. In this lecture, I'm going to be thinking generally you need to gain skill at that as well. It's good to both look at particular examples with particular numbers and gain skill at doing what I'm doing here, thinking more generally where m, b, and k in this case are arbitrary. What would happen if I had converted this to a first order system? Define the velocity to be dy dt right away. What would the eigenvalues be? From what we've done recently, you know that you need to use the quadratic formula or factor to find the eigenvalues. Could they possibly be the same numbers? Let's see. Here's the corresponding first order system. The first equation is just a definition of the velocity as the rate of change of the position of the mass. So the first equation becomes dy dt equals v. The second equation, dv dt, comes from the original second order equation here. Divide everything by m, and then solve for the second derivative of y with respect to t, which is the same as the first derivative of v with respect to t. You'd get a negative k over m times y on the right side, giving you this term. And you'd also get a negative b times v. b over m times v on the right side, giving you this term. All right? We can write that in matrix vector form, or we can say what the coefficient matrix is. It's this A. This would be the coefficient matrix for this. Careful. It's easy to make a mistake on this. Little y is the first variable, little v is the second. So when you see a v there, it's got to correspond to a 1 in the second column of the first row. And it's best to put y first and the v second down here so that you get these numbers in the right order. You know, technically speaking, in this equation, you could switch these around, but you do not want to switch these around in the matrix because y is the first variable and b is the second. All right, so what's the characteristic polynomial? Use the trace indeterminant. Lambda squared minus the trace times lambda plus the determinant, like we saw, is lambda squared. What's the trace? Add the numbers on the main diagonal. 0 plus negative b over m is negative b over m. I'm subtracting the trace times lambda, so that I ultimately get plus b over m times lambda. And what's the determinant? The product of these two is 0, minus the product of these two is going to be plus k over m. Hey, doesn't this kind of seem familiar in a way? Think about that second order differential equation and divide everything by m, and you'll see a similarity. Set this equal to 0 and solve for lambda with the quadratic formula, getting negative b over m plus or minus square root of b squared over m squared minus 4 times 1 times k over m, all divided by 2 times 1. Right? That's just the quadratic formula. They take negative of that, plus or minus square root of that squared minus 4 times 1 times k over m gives you this, all divided by 2 times the coefficient of lambda squared, which is 1. This can be simplified to negative b over 2m plus or minus the square root, well, put a 1/2 in front, the square root of, get a common denominator of m squared here, and you're going to get a b squared minus 4mk over m squared. Square root of m squared in general is the absolute value of m, but hey, m is positive, so I don't need absolute value signs. I can write this as negative b over 2m plus or minus 1 over 2m square root of b squared minus 4mk. And then I can write this as one fraction, negative b plus or minus the square root of b squared minus 4mk divided by 2m. Where have I seen that before? Isn't that familiar? It's right there. It's s. The two possible values of s in general. It's the same thing. The dot, dot, dots means there's work missing. That essentially is the work. The lambdas for A, the eigenvalues for A, are the same as the S values for the second order equation. It's no coincidence. That had to happen. So now we're going to consider a bunch of special cases. Undamped, no friction, not realistic, but we'll consider it anyway. Underdamped, a small amount of friction. Critically damped, a critical amount of friction? Yeah, in a way I'll describe. And overdamped, a lot of friction. It's easiest to think about the overdamped case first. Then I'll jump to underdamped, then I'll jump to undamped, and then at the end it's hardest to think about the critically damped actually. So again, I'm talking general properties here. My students, and anybody else out there, should work on examples as well. I'm going to solve infinitely many problems at once, essentially, by talking about generalities here. First case, if the eigenvalues lambda 1 and lambda 2 are real and distinct, in other words, if the thing under the square root is positive, which is equivalent to b squared being bigger than 4mk, I'm talking about right here, then you're going to have two real eigenvalues, because you're going to get a plus or minus a square root of a positive number, which will be a positive number, negative b plus or minus some positive number over 2m. It turns out that these will be negative eigenvalues. We're talking harmonic oscillator here, where m, b, and k are all positive. And you can check, no matter what happens there, as long as b squared minus 4mk is positive, this is going to give you two negative numbers. Intuitively, the square root of b squared equals the absolute value of b. If m and k were either of those were 0, the top could become 0. Negative b plus b would give you 0. But because we're subtracting 4mk in there, which is non-zero, we do have a mass and we do have a spring, is what that means. The square root of this thing will be actually smaller than the absolute value of b, and when you do negative b plus or minus that, it will not become positive, is what I'm trying to say. So you're going to get two real negative eigenvalues for harmonic oscillators in that case. What's the general solution? It's this. And again, I'm assuming lambda 1 is negative and lambda 2 is negative. I could have written that as negative something times t here and negative something else times t. And if I did that, then the somethings would be the opposites of the eigenvalues. So just keep that in mind. Lambda 1 and lambda 2 are both negative, and therefore this whole thing decays to 0 as t goes to infinity. These go to 0 pretty quickly, in fact, in general. There's essentially no oscillation. There's no cosines or sines. Okay? When we do the complex non-real case, I am going to use negative signs to emphasize certain things are negative, so just be aware of that. Whereas here I'm not. I'm just writing over here that lambda 1 and lambda 2 are both negative, and I'm saying they're both negative here. That's a scalar solution, scalar general solution of the original second order equation. You can definitely use that to solve initial value problems for second order equations without ever using matrices or vectors. And if all you're after is the position y as a function of t, that's good enough. You do not have to use systems, matrices, vectors, that kind of thing. It's not necessary. Okay, that's the big thing. Sometimes people think that they always have to use the matrices, vectors, and eigenvectors and eigenvalues. You don't always have to. You would need two initial conditions to solve for k1 and k2. You need an initial position and initial velocity. Y of 0 equals something, and y prime of 0 equals something. Then you can solve for k1 and k2. And the graph is going to be an ordinary graph in a ty plane. Ordinary kind of graph, not a parametric curve in the plane. Corresponding general solution, if we did convert to a first order system, I'm going to show you, I could convert to the system first, try to find the eigenvalues and eigenvectors and write this down, but that's not what I did here. I took a quicker way. I know my system vector solution, capital Y, has got components little y and little v, where little v is the derivative of little y. So what I did was I just differentiated this, called it v, and put it in a vector, like this. Right here, this matches the first component, which is y. To get the second component, v, all I did was I differentiate this with respect to t. You get an extra factor of lambda 1 here and an extra factor of lambda 2 there because of the chain rule, and you see that here. And then, as we often do, we can separate this into a linear combination. k1 e to the lambda 1t times the vector 1 lambda 1 plus k2 e to the lambda 2t times the vector 1 lambda 2. Lambda 1 and lambda 2 are eigenvalues. Are these two things eigenvectors? Yes, they are. This is an eigenvector for that eigenvalue. This is an eigenvector for that eigenvalue. Remember, they got to go together. Each vector is an eigenvector only for one eigenvalue, not for both of them. And lambda 1 and lambda 2 are negative. This is going to approach 0, and we've seen that it typically approaches 0. By typically, I mean for most initial conditions. For random initial conditions, it will. Along the eigenvector, corresponding to a straight line solution, in fact, whose eigenvalue is closest to 0. It approaches 0 as t goes to plus infinity. Let's try to draw a picture now. So what do we have going on here? This is going to be the phase plane. Don't label it x and y, label it y and v. There is going to be a unique equilibrium point at the origin. And these eigenvectors, for the corresponding eigenvalues, lambda 1 and lambda 2 are negative. They're going to point southeast, because lambda 1 and lambda 2 are negative. The first component is 1, the second component is negative. And let's just pretend lambda 2 is closer to 0. So lambda 1 is less than lambda 2 is negative. The one that's closer to 0 is going to be not quite as steep. If lambda 2 is closer to 0, that vector will not be as steep as this one. So maybe the one for lambda 2, lambda equals lambda 2 is there, and the one for lambda equals lambda 1 is like this. Along those lines, you'd have straight line solutions going to the origin. Elsewhere, the other initial conditions give you solutions that approach this line for lambda 2 instead of the other line for lambda 1, because lambda 2 is the one closer to 0. And what that's going to mean is the other solutions are going to look about like this. They're going to be tangent by approach along the eigenvector. They're going to be tangent to that eigenvector's direction. You're going to get solutions. These do get a little tricky. Look about like this. It takes practice to get better at this. I'm actually sort of secretly using the null lines without telling you. Get a picture that looks about like that. So while there's kind of a partial oscillation, almost an oscillation in the y and v values, no literal oscillation goes on. Y does not oscillate, y and v do not oscillate around the origin here. Where are the null lines? I'll show you those in the picture here in a second. Indeed, these constant vectors are eigenvectors for the corresponding eigenvalues. And we can check that by taking a times one of those eigenvectors. If a times that eigenvector is a multiple of itself, it means it's an eigenvector. And it's certainly non-zero. So it's an eigenvector. Here's a, multiply. Take the first row, dot it with this column. Get 0 times 1 is 0, plus 1 times lambda 1 is lambda 1. Take the second row and dot it with this column vector. Negative k over m times 1 is negative k over m. Minus b over m times lambda 1 is minus b over m times lambda 1. And then I do a little trick. I can replace negative k over m minus b over m lambda 1 with lambda 1 squared. Why can I do that? Because lambda 1 is an eigenvalue and it's satisfied lambda squared plus b over m lambda plus k over m equals 0. And so I can solve this equation for lambda squared, or lambda 1 squared if I'm thinking about lambda 1. It equals this, and so I can make that substitution. And then I can factor out a factor of lambda 1, so I got a scalar times the original eigenvector. These two things match. That means 1 lambda 1 is an eigenvector for A with eigenvalue lambda 1. Same calculation, except change all the subscripts from 1 to 2 would verify that that's an eigenvector corresponding to that eigenvalue. Because of the lack of the decay and the lack of oscillation, this is called the overdamped case. A lot of damping. B, the damping constant, is relatively large enough to make this true. Which would also, of course, mean, since B is positive, B would have to be bigger than 2 times the square root of m times k is another way to think of it. B would have to be bigger than 2 times the square root of mk. B can't be negative. Overdamped, a lot of damping, no oscillation. The no lines are these two things. The y-null plane is the y-axis, so I did purposely try to make these solutions cross that with vertical tangents. Other solutions cross it with vertical tangents as well. And the v-null plane, which you cross with horizontal tangents, is this line. And it's going to turn out that's going to be about like this. This picture, approximately like this. And notice those solutions are crossing that with horizontal tangents. And all solutions have to cross that with horizontal tangents. Okay, so a bit fuller picture of the phase plane. What about underdamped? A small amount of damping. Underdamped doesn't mean undamped. There will be damping, it's just relatively small. B is positive, but not too big. In that case, the eigenvalues are going to be non-real complex numbers with non-zero imaginary part, is what I'm trying to say ultimately by saying non-real. And they're going to be complex conjugates of each other. They're also not going to be purely imaginary numbers on the imaginary axis because there is damping. And what this is ultimately going to mean intuitively is cosines and sines will be involved in the formula for solutions, and there will be oscillations. Underdamped is a small amount of damping, not enough to erase the oscillations. B has to be still positive, but it's not too big. B squared must be less than 4mk, which means B is less than 2 times the square root of m times k. And we can write the complex numbers, eigenvalues, in this form, negative alpha plus or minus beta I. And in writing this in this way, here's where I'm assuming alpha is positive so that negative alpha is negative. And that's a negative real part. And if you look back at the quadratic formula, alpha would be b over 2m, because the quadratic formula gave us negative b over 2m as the part before the plus or minus. I got a negative alpha there. And the beta is going to be this. And notice that I actually switched around the order of the things under the square root. In the quadratic formula, we got the square root of b squared minus 4mk. So why did I switch it around? It's because I essentially factored out a negative 1. A square root of negative 1 is I. You see the I there? Beta is the imaginary part of this, or plus or minus beta is for these two eigenvalues. It's a real number, though. So I have to take a square root of a positive number for beta to be real. The I is just next to the beta. To say it's not purely imaginary here means alpha is non-zero. In fact, alpha is positive, B is positive, so we have some damping. Once again, Euler's identity comes into play as it did in lecture 23a. We did it with eigenvalues and eigenvectors in 23a. Now we're doing it with a scalar solution. You can still use Euler's method. You can still come up with a YC function that's going to be a complex solution, algebraically speaking, of the differential equation, even though it's not clear how you would visualize such a thing. But if we use properties of exponents and also use Euler's identity says that e to the I times beta t is cos beta t plus I sine beta t. I also multiplied the e to the negative alpha t through, if you imagine, I did 2 steps there essentially. Initially you'd have e to the negative alpha t times in parentheses cos beta t plus I sine beta t. Then I multiplied the e to the negative alpha t through. And both these things right here and here are real quantities. YRE is the real part, YIM is the imaginary part, but once again, imaginary parts are not imaginary numbers. They are real numbers that are just next to the I in the complex quantity. And just as with the vector case, those two real functions will be two linearly independent solutions of the differential equation. And a general linear combination of them will be a general solution. That takes verification. We verified it for the vector case last time. Okay, that's pretty amazing that that works. It's pretty nice that it works. We're glad. Again, the solution space is going to be two-dimensional. Knowing these are not scalar multiples of each other says they're linearly independent. And therefore, they will form by the basis theorem, a spanning set for the solution space and also be a basis. And this is a general solution. If we convert it to a vector in the same way I did in the last example, by putting this in the first component and differentiating it to get the second component, the velocity, it's kind of messy, but you get this. You do need the product rule as well as the chain rule. And you should probably pause the video and take 5 minutes to verify this. That this is the derivative of that, v and y, and that you can rewrite it like this too if you want. There is exponential decay. Alpha is positive, so that negative alpha is negative. This decays to 0, and this decays to 0. But because of the cosines and sines, there's still oscillations. The solutions in the phase plane oscillate around the origin. They spiral in toward the origin. The origin is a spiral sink because the real part of the eigenvalues is negative, like I said in the first slide. Yeah, and this is a small amount of oscillation, or small amount of, what I mean to say, a small amount of damping. It's underdamped. It's weak enough damping that there's still oscillations. Mass moves back and forth, but the amplitude gets smaller and smaller. All right, the two more special cases include an unforced undamped harmonic oscillator. Well, we're still talking about unforced, so there's no external forcing. But now it's undamped as well. No damping, no friction, not realistic, but still worth studying anyway, as maybe an approximation to what happens if the damping is really, really, really super tiny. These can be good approximations. The eigenvalues in this case are purely imaginary numbers. The damping, B, is 0. There's no damping. In the quadratic formula, the part before the plus or minus goes away, because that was negative b over 2m, and b is 0 here. So we get really just a plus or minus a square root of a negative number divided by something. The eigenvalues are plus or minus beta I, where beta is the second part of the quadratic formula, square root of 4mk divided by 2m, and I plugged in b equals 0 under the square root here as well. That simplifies to this, and then that is positive. Euler's identity gets us a complex solution. Take the real and the imaginary parts as linearly independent solutions of the original equation, and therefore a linear combination of those is a general solution of the original. You should practice solving some IVPs, some initial value problems with this as well. Okay, it's not too hard, but make sure you can do it. We can once again convert it to a vector, like this, where once again the second component is the derivative of the first, because the velocity is the derivative of the position. Oh, and there's a typo here. Forgot to delete these e to the negative alpha t's. Those should not be there. Okay? Pure oscillation, no damping. Oscillations with no decay. Undamped. Undamped is no damping, no friction. Underdamped is a small amount of damping, a small amount of friction. Overdamped is a lot of friction. What's the boundary between undamped and overdamped? It's called critically damped, because it's the boundary, it's the critical point, so to speak. It's analogous to a bifurcation value. In fact, you could even say that a bifurcation occurs at this transition between underdamped and overdamped as B increases. I'm calling it an analytic bifurcation because it's a bifurcation in the formula from one in the underdamped case that has cosines and sines to one in the overdamped case that has no cosines and sines, only exponential decays. Analytic referring to formulas, essentially. I could call it maybe symbolic as well. There's going to be other kinds of bifurcations we're going to talk about soon. that are called topological bifurcations. And in a nutshell, a topological bifurcation does not occur when you go from underdamped to overdamped spiral sinks to non-spiral sinks, say, because it's still a sink. Topologically, it doesn't matter whether it spirals or not. This critically damped case is important, theoretically speaking. However, you never really observe it in a real-life situation. You never observe the undamped case either. Why? Because it occurs exactly when this equation is exactly true. The square of the damping constant has to be 4 times the mass times the spring constant exactly to be in the critically damped case. And in real life, exact equations like this with masses on springs would never happen. Not exactly. It would occur with probability 0. Is another way to think of it. In this case, though, if we're thinking about it theoretically, there's just one real eigenvalue. It's the first part of the quadratic formula. The plus or minus square root goes away because the square root is 0. It's a real number, one real number, but it's got multiplicity 2 in the characteristic polynomial. That means you'd be able to factor the characteristic polynomial as lambda plus b over 2m quantity squared is the way you'd be able to factor the characteristic polynomial in this case. As far as finding solutions, it's trickier. It turns out that this is a general solution of the second order equation. And the tricky part is this extra t that comes into play right here. That's the tricky part. Now, in the textbook that we use, Blanchard, Devaney, Hall, they do examples like this from time to time, and they do say, well, let's just try adding an extra t there. And essentially, it is like just guessing, and it works. Okay, you can check it out. It still decays to 0 as t goes to infinity because you still have an exponential decay here. Lambda is negative. I didn't really mention that, but lambda would still be negative. I could have written that here. Convert it to a vector form, differentiate the first component to get the second component. You could write it in one of these ways, in vector form. Notice that if I decide to write it this way, this is not a constant vector. It is a way I can write the solution, but that vector involves time t. It's not constant. So it's not really an eigenvector. Now, this case is trickier. If you read section 3.5 of the book, they approach it differently than what I'm doing here. I will briefly talk about that next lecture probably, but here I'm just saying you can write it like this, but it's not really an eigenvalue, or not really an eigenvector here. Oh, there's another typo here. This lambda 2 should just be a lambda. In the case of one real eigenvalue that's a double root of the characteristic polynomial, there is still just one line of straight line solutions corresponding to this thing, which will be an eigenvector of the corresponding system. But there are no other straight line solutions in that case. Thanks for watching.